So welcome to the last session for today, and give a nice welcome to Vincent O'Dea from Fujitsu, talking about evolving landscape of a Postgres logical application, I guess.
Yeah.
Thanks.
Thank you. Yeah, so thank you. My name's Vince O'Dea. I'm from London, and I'm here to talk about logical replication. Hopefully you can all hear me okay. So I've been working on databases now, in architecture and engineering and, of course, DBA roles for over 30 years now. And predominantly working, obviously, on Postgres, Oracle, SQL Server, Sybase, and various other databases in that time, and, of course, replication for all of those platforms. So we're here today to talk about, I'm going to be talking about conflict management, parallel apply, table and column exclusions, and seamless cluster upgrades, and slot synchronization for high availability. So before we delve into conflict management, I'm just going to spend a minute just going over what logical replication is. I'm sure you all know anyway, but logical replication uses a publish and subscribe methodology, and it allows you to be more selective with what you're replicating when you're copying data between databases. And whereas physical replication copies data at a block level, of course, logical replication is decoding this, and it is turning it into, if you like, the DML, as it were. And this is copying at a row level. So it gives us more control and granularity over what we're actually copying, and it's obviously useful for things like converting to different formats. If we're taking data out of Postgres, possibly to another external system. Then it's also good for specifying what rows and what columns we're going to replicate or copy. And it, of course, significantly with logical replication, it means that the subscriber allows writes. So, whilst this allows writes to the subscriber, it nicely leads us into our next slides, which is, of course, that by allowing direct writes to a subscriber, it can introduce problems. So, and of course, a conflict. So a quick conflict example. You can see here we've got two nodes. We've got a publisher node and a subscriber node. And you can see, and you've got a user writing data into a table on the publisher node, and an insert is made on the publisher side, and this has a primary key, and of course this gets written to wall, and before it actually gets applied over onto the subscriber, another user on node 2 directly writes a row onto the same table using the same key. And of course, this then means that the apply fails, and this is what we mean by an example of a conflict. So as you can see, we get an error, replication fails, because we had a duplicate key constraint violation. And this is a typical example of a logical replication conflict. So a conflict can occur when a change from a publisher being applied to a subscriber database violates a constraint like a unique key constraint. And a conflict occurs when incoming changes from a publisher fail to be applied on the subscriber due to a data difference. And broadly speaking, we've got three different types of conflicts. We've got the conflict type where an insert already exists because of an existing row. We've got an update conflict where a update, if you like, modifies an already updated row. And we've also got delete conflicts where a delete occurs on a modified or missing row. And prior to Postgres 15, conflicts weren't handled very well. One of the major problems was that whenever there was a conflict, the apply worker exited, and the apply worker would retry. It would start up again every few seconds and retry the same change, of course failing each time, in an infinite loop until you took some action. So you either manually disable the subscription or took corrective action steps. And prior to Postgres 15, update and delete conflicts due to missing data on the subscriber were also silently skipped. And so any conflict resolution had to either be done manually or to prevent a retry loop. Or you could use an automatic solution. You could use a before trigger. And although there were functions like PG replication, origin, advance to do this, this was quite dangerous, and it was also quite laborious because in order to use it, you needed to know what the next LSN would be. And of course, it wasn't as intuitive in order to be able to work that out. And you also had to know what the origin was as well. And you couldn't get these from the logs, so it was harder to do that. And so you had to use PG logical slot peak to be able to see what the next values were. So it wasn't easy, and it was a bit risky because, of course, if you were to enter an LSN that was above the intended LSN, then potentially you could lose data. And so since Postgres 15, one of the improvements was disable on error. And so this option allowed a subscription worker to automatically break out of a restart loop and disabling the subscription. And so this avoided the continuous loop. And another improvement was the auto-subscription skip LSN, which obviously was safer, because you'll notice that instead of actually telling the apply worker process where to resume from, you're telling it the actual failed LSN in order for it to skip. So it's safer, and also it has some checks in there to make sure when you use it that you're actually resuming the LSN, you're skipping the LSN that actually failed. So it also, Postgres 15 also introduced the PG stats, subscription stats, and that was a view on the subscriber for tracking errors. So you can see that we've got 3 columns, and so these columns are able for each subscription to tell us how many errors we saw with the actual copy data synchronization, and how many perhaps we've seen with the apply. And of course they can be reset. So also significantly, the error logging was more verbose. You can see that now, since 15, that we're able to get the actual origin for the failing transaction. And we can also get the finished LSN. So in other words, the LSN associated with the commit of the incoming transaction. And with these additional details, we can more easily use the PG replication origin advance function, should we still want to do that. But equally, we can use the auto skip, the auto subscription skip. And in the next few slides, we'll look at a conflict error and resolution steps. So in this scenario on the publisher node, we create a table called tab with just 1 row, and the value 5 was pre-inserted before creating the subscription. And on the subscriber, we create the same table as on the publisher, because of course DDL doesn't get replicated. But notice on the subscriber, the same table has a unique key constraint, and on the publisher, we don't have any constraints. So that's another feature of logical replication in the sense that that both the source and the target schema of the table don't have to match. So, and also you can see that the disable on error is equal to true. It has been enabled on this one. So here we can see transaction 1 just inserts the value 1. And then transaction 2 is inserting values 2 to 8. And then transaction 3 inserts the value 9. And we see the table on the publisher shows 10 rows having performed those 3 transactions. If we look at the subscriber, then we see, first of all, before we look at the subscriber, we can see that the PGStat subscription stats is telling us that we've had an apply error. And when we have a look at the actual contents of the table, we can see that we had the pre-inserted row 5 and just the transaction 1. And that's obviously because transaction 2 failed, and we are obviously preserving commit order in any of our replication. So the error in the message on the subscriber PG log shows us that key ID 5 already existed, and it also shows us the origin that caused the conflict and tells us the finished LSN of the conflicting transaction. So those 2 new details added in from PG15, that these are what's required to run the PG replication origin advance. But as I said, we could also just skip the LSN that failed, involved with the failed transaction from 15 onwards. So here in this example, we're just using the PG replication origin advance function to move replication forward. And of course, in doing this, we have to, once we know the LSN with this function, we have to increment the value of the LSN so that it knows where to resume from. And as mentioned, that since 15, we could have got the same outcome if we'd skipped the failed LSN using the auto-subscription skip. And obviously, there's no manual LSN calculation that could have gone awry. So these are, of course, other ways. There are other ways of resolving replication issues. One of them, as I mentioned earlier, is to have created a before trigger, which is if you know what custom policy you wanted to implement, then of course that was another option. And this slide shows the, if you like, the disadvantages of the current conflict resolution methods. You can see that there's skipping transactions can result in a loss of data. Skipping requires constant monitoring, and also there's going to be learning time in implementing avoidance methods, like we talked about possibly with the triggers. And of course, that there's a performance overhead if you did implement triggers onto conflict resolution. So since Postgres 18, there have been some enhancements in the conflict management, and you can see that we've got 7 new conflict handling types. And these are insert exists, update exists, update origin differs, update missing, delete origin differs, delete missing, and multiple unique conflicts. So we're going to take a look at these in a little bit more detail. So insert exists and update exists from Postgres 18. So when inserting or updating a row violates a non-deferrable unique key constraint, the result is an error is raised. And it's the same behavior, but the key difference is that we're now getting extended log information. And with to get the most out of your, if you like, logging to the Postgres log, you really want to enable the track commit timestamp parameter on the subscriber. And that way, of course, we get the timestamp of the subscriber transaction. And so what's new is seeing the schema name and the table name and where the conflict happens. And we can note whether it's an error or an informational log message. And we can see the conflict type, which you can see here is insert exists. And also the error message at the very beginning. We can see more details about the key already exists. And you can see the local tuple value where the external or the remote incoming tuple had the conflict. So the next conflict type, update origin differs. Again, it's another new one. Previously, conflicts were treated as constraint violations, but not all conflicts were constraint violations. So an example might be if the subscriber had been modified locally in between updates from the publisher. And a change made locally has a null origin. A change applied through logical replication subscriptions will have the origin of the subscription. And note the default action for update or delete origin differs is to commit the transaction, but additionally now a detailed message is logged. So you can see that it's actually either logging when it's informational or if it's failing that it's an error. So Postgres 18 introduced conflict types for update missing and delete missing for when an update or a delete operation is on a row that doesn't exist on the subscriber. Previously, it was silently skipped, and from PG18, it's the same behavior. It's still skipped, but it's no longer silent. We're getting the additional information that you see on the slide. And multiple unique conflicts, lastly, is for when a conflict caused by any insert or update that spans multiple constraints in this categorization. It still requires manual intervention, but all the pertinent information for each of those conflicts is now being logged. So disclaimer here that in terms of future enhancements, these are not yet released, and the community can decide to reject or redesign. But what's already already developed and but not as part of the official release, is enhancements for detecting and resolving conflicts. And these will include a new conflict type of update deleted. And this conflict arises when the local tuple to be updated has already been deleted by another origin. So this conflict type will provide details on how and when the deletion occurred. And the update missing users can't currently distinguish between two possible causes. Excuse me, sorry. With only update missing users can't distinguish between if the insert record has not been applied. In other words, it didn't know if the update that it's trying to perform is on a record that has not yet been inserted, or if the local tuple on the subscriber has already been deleted, hence the conflict type. So this slide describes how it should work, and you can see when the logical replication apply worker applies the remote update from the publisher, it first searches for the local tuple to update. If it finds it, then there's no conflict. Apply the update, everything's okay. But if it can't find the row, then it performs some extra work. to check if the tuple was recently deleted by searching the dead tuples for the old value from the remote update. And if it finds a matching dead tuple, then it will log the conflict as update deleted. And if the old value is not found in the dead tuple, then it will log the existing conflict as update missing. So this slide shows how the update conflict would be seen in the Postgres log. You can see it's an informational log, and the context showing the origin of the source, and the details on the locally deleted tuple that caused the update to be skipped. And as an example, the proposed update delete conflict would be useful if you wanted to keep changes based on last update wins resolution strategies. It would still involve a manual task to resolve it, but it would, at least at this stage, give you some insight into what happened. And in this bidirectional example, a user deletes a row on node B, and concurrently another user updates the same row on node A. And in step 3, it tries to replicate the update from node A to node B. The apply worker detects a conflict, and because it cannot find the local row to be updated, it detects and reports the conflict. And in this scenario, the user wants to maintain data consistency using a time-based resolution, keeping the change with the latest timestamp. The last update wins. So if the remote update occurs earlier than the local deletion, then the update on node B should be skipped, keeping the latest change. Alternatively, if the remote update occurs after the local update, after the local deletion, we need to apply the update. And we'd need to convert the update into an insert and apply the row into node B. But currently, this is only conflict detection. The resolution side is still not officially released or approved. So, update deleted is proposed would allow you to detect and manually resolve the conflict appropriately to achieve the data consistency that would not otherwise be possible. And dead tuple retention, the update delete resolution method relies on the required dead tuples still being present and not having been removed by vacuum. And retaining these tuples on the subscriber sees the introduction of a new subscription option called Retain Conflict Info. But that's now, been renamed to Retain Dead Tuples, I believe. But we can't retain dead tuples forever, or it would affect the performance, storage required. So this option, dead tuples, are retained for the duration of applying and flashing all the remote transactions that occurred concurrently with a local delete. And dead tuples on the subscriber are retained before applying and flashing all the remote transactions that happen concurrently with the local delete. And the concept is that this is enough when using a time-based resolution method, such as last update wins or oldest update wins. And if no dead tuples are found, then it means that the local delete happened before the update. This means you're aware of what happened and can choose the appropriate resolution method. So this is the dead tuple retention workflow. A replication slot is created by the logical launcher on the subscriber with the latest transaction ID to retain the dead tuples. And a back-end delete with transaction ID 899 runs on the subscriber. The apply worker wants to advance the transaction ID in the slot past the delete transaction ID, so it checks the publisher wall sender if there were any in-flight transactions. It sees an in-flight replicated transaction on the publisher with transaction ID 766, so it waits and then retries. It's waiting for LSN 1566D10 to be applied. And when it sees the publisher concurrent transaction has been applied, it can advance the transaction ID in the slot, which then allows the vacuum to remove the dead tuples. So it's periodically advancing dead tuple replication slot on the subscriber, and this allows the unnecessary dead tuples to be removed by vacuum. But of course, we can't retain dead tuples forever. So the proposal is for an automated way of preventing indefinite retention, and that's the max conflict retention duration. And this parameter, if applied, it just means that in the event that the transaction, the apply worker doesn't process fast enough to advance the slot within the period specified, then the replication slot will be invalidated. And this will, of course, allow the dead tuples to be removed through vacuum. So that's all for the proposed update deleted conflict type. And again, disclaimer that these are not yet released to the community, and the community can decide to change its mind or redesign. Currently, Postgres only supports conflict detection, and under development are mechanisms to automatically resolve conflicts based on config and conflict types, where we provide built-in conflict resolutions to reduce the manual effort. And the proposal is that the users choose the appropriate resolution method for conflict types, depending upon their own personal preferences. And the goal being to achieve eventual bidirectional consistency. So here's how conflict resolution could be used by adding our preferences into the subscriber config. So you can see the create or the auto subscription, and we're defining a conflict type. In these subscription statements, we specify whatever the resolution or resolver for each should be. And these next couple of slides show the proposed resolver methods and the potential conflict types that they can be used for. Resolver is the resolution method, and the description is the outcome. And applicable conflicts are the list of conflicts for which you could choose to map it. And so this is the list goes on. We had apply remote, apply or skip, apply or error, keep local, and then we've got last update wins, skip, and error at this stage. So basic workflow for the last update wins. So this slide is an example where we can see how it resolves an insert exists. Before applying the remote insert, the logical replication apply worker checks if any conflicting tuples with the same primary key exist. And if they do, the apply worker gets the commit timestamp and compares the commit timestamp of the local tuple with the commit timestamp of the remote insert. And if the local tuple commit timestamp is later than the remote commit timestamp, then the remote insert is skipped. Otherwise, it will create an update to change the value, or it could create an update to change the value of the remote tuple to match the remote new value. So again, still under design, we see a potential new resolution resolver called Delta resolution. And this conflict resolver could be useful when two different nodes update a row with two different values. And in this example, a user on node B updates the balance field from $100 to $300. And at the same time, another user on node A updates the same field from 100 to 200. And if we use a time-based resolution, then the result will either be $200 or $300. But it's possible that there's a scenario where we want to retain both increments and add the difference to a combined update instead of just choosing one of them. For example, the extra $100 from node A and the extra $200 from node B is an additional $300. So the final result would be set to $400 using this new proposed conflict resolution type. So that's advanced. So that's improvements in conflict handling. And now it's going to take a look at parallel apply. And parallel apply, there are also plans to offer. Before I get into that, users more flexibility by supporting user-defined conflict resolvers. In which case, users can write their own conflict resolutions through user functions to suit their own business rules. And also to enhance monitoring, there's plans to add detection and resolution history table. And this table is going to log all the detected conflicts along with the resolution methods used for each, assuming, again, that this is approved. So that's all on the new logical replication features related to conflict handling and plans. So initially, obviously, handling the conflicts was difficult, but these enhancements help in understanding what's happened in a more user-friendly way. And the future plans are for potentially more automation of conflict resolution. So, parallel apply. From the beginning of logical replication, the subscriber used a single threaded apply worker process, and all transactions were processed sequentially. The apply worker had to wait for the transaction commit message to be sent from the publisher before beginning to apply the changes on the subscriber. And this, of course, could introduce lag when dealing with large transactions. But from PostgreSQL, we saw the introduction of the parallel apply for streaming large transactions to the subscriber. And in progress, large transactions could be broken into smaller chunks and be streamed from the publisher to the subscriber. So on the subscriber, a leader apply worker coordinates parallel apply workers and only commits when it's received the commit message from the publisher, and all workers have also completed. And this, of course, avoids the delays waiting for the entire transaction to complete before processing. So to enable parallel apply, we had to set some parameters, and max parallel apply worker per subscription, and max logical replication workers to improve the degree of parallelism that we wanted to use, and obviously to define the pool size from which to draw from. And then we manually added the subscription option to streaming equals parallel. And in PostgreSQL, the ability to use to introduce parallel apply was introduced for streaming large transactions and to apply in parallel without needing to specify the version 2 protocol like you could from Postgres 14. And from PG18, parallel apply becomes the default behavior for large transactions. And from 19, the intention is to make parallel apply the default for all transactions. So this slide shows the subscriber's parallel apply workflow. The wall sender process on the publisher is decoding, and raw wall records as part of the logical decoding into a logical format and stream to the decoded changes onto the subscriber. And streaming is triggered when a transaction commits or when the logical decoding workmem limit is exceeded. And when the first stream of a large transaction arrives, the lead apply worker assigns parallel apply workers if available, and at publisher commit time, the lead apply process waits for all the parallel apply workers to finish to ensure that the commit order is preserved. So this next slide is comparing elapsed time between a synchronous single-threaded and parallel apply setup for an insert workload. And in this test, that there were 1 million rows incremented during 10 cycles into a single table. And as you can see, that the elapsed time from the insert to commit halved 120 to 60 seconds when applying the same workload with parallel apply. This next slide is another parallel apply comparison using a different workload, comparing the effect of increasing the logical decoding work memory from 10 to 60 meg. And you can see the elapsed time under the parallel apply consistently outperforms serial apply, regardless of the different 10 meg increment size of logical decoding work mem. So we can see the elapsed time for parallel apply about half that for sequential serial apply. So as mentioned, as from PG19, the intention is to make parallel apply the default. And this slide just summarizes the reasons for changing the default parallel apply for all transactions: improve throughput, reduce latency, scalability, dependency management built-in methods to ensure consistency by delaying only conflicting transactions. And also, the idea is it will have a seamless failback. In other words, if no parallel workers are available, the lead apply worker process will still run in a single-threaded manner. So one of the, that I don't think this has been approved yet, but from Postgres 19, table exclusions is hopefully going to be happening, going to be introduced, and just a little bit about what purpose this solves. From Postgres 10, you've been able to create a publication for all tables to replicate application tables in the database for convenience instead of having to manually list. And of course, for all tables, it publishes changes for all tables across all schemas in a database. And new tables are automatically added into the publication. And that includes columns as well. So it's more of an all or nothing with the current for all tables approach. And once you've created the new tables or columns on the publisher and subscriber, you refresh the subscription to incorporate the changes. But because logical replication doesn't replicate DDL like alter table, add column, for schema changes, you had to run the DDL to create whatever it was that you were adding onto the subscriber manually. And PG15 also introduced for tables in schema, which publishes changes for all tables within one or more schemas in the database. And this included any new tables added to the specific schemas. And schema changes, just like with for all tables, required running the alter subscription refresh on the subscriber for it to detect and process replication for them. So that was what we had up to date. But you've also been able to create a publication for all tables to replicate application tables, and you could do this for all tables or otherwise. Sorry, I'm repeating myself. So again, disclaimer alert, this proposal is not yet released, but we expect it to be, it's targeted for PG19, and you can see here that the new accept table clause that is targeted. And currently, if you want to exclude tables, you have to either list all the tables that you do want or move them to a different schema and omit them from a full tables and schema publication, but neither of those are ideal. So the new accept clause enhances control over what data is published and replicated. And we can use accept table for table exclusions, for all tables, replicate it every application table so in other words, we can, before we had to replicate every table in the database, but now we can say for all tables, but we can say except for table T1, T2, etc. So in other words, this allows us to skip sensitive or unnecessary tables. And the benefit, of course, is that it provides a simple syntax while allowing us to quickly exclude non-essential or private tables. And we can also accept columns. The plan is to also be able to skip columns from being replicated as of PG19. So that if there are any columns that contain sensitive information, that they can also be, that they don't have to be replicated. So the overall improvement is it just gives us more granular control over replication and allows us to reduce the overhead where it wasn't necessarily, and also to improve security for sensitive columns or tables. So one of the other features is seamless replication cluster upgrades. And before Postgres 17, major upgrades interrupted replication. Slots were lost, writes had to be paused until setups were manually reconstructed. So for in-place upgrades using the built-in PG upgrade, the weaknesses were, first of all, downtime, and secondly, breaking streaming replication. Because streaming replication requires the Postgres major versions to be matching. And prior to PG17, logical replication slots aren't migrated as they were treated as non-specific, as node-specific and ignored by PG upgrade accordingly. So before Postgres 17, you disable and drop the subscriptions, and after the upgrade completed, you had to rebuild the replication setup. And this would be done offline with the application rights stopped prior. But from PG17, PG upgrade has been significantly improved for logical replication. And PG upgrade now migrates logical replication slots, which preserves the subscription states during the PG upgrade and avoids having the time associated with manually having to redefine the logical replication slots. So this allows logical replication to resume seamlessly after the upgrade by adjusting the subscription connection details for the new publisher. And from Postgres 17, we can use these new logical replication features for the ability to perform an online replica upgrade of a logical replication cluster and an upgrade of a physical standby by temporarily converting it into a logical replica. So in the first use case that you can see here, it's a logical replication setup. And you can see that in this case it's unidirectional, but so what it means is that you've got potentially all of your users accessing just node 1, but we're still replicating the logical replication over to node 2. And then you can see in step 1 the subscription is disabled. In step 2 the publisher is stopped and upgraded to PG18. And the new PG18 version publisher is started. And then in step 3, the subscriber is stopped and upgraded to PG18 using PG upgrade and started up as a PG18 instance. And step 4 may not be required depending upon what happened with your application while we were performing the upgrade. So in other words, if you didn't create any new objects. This may not be required, but if no application tables were added or modified in step 1, you didn't have to do this. But if it is, you'd have to create the new tables on the subscriber, which were added to the publisher since the process started. And then, of course, you'd have to refresh. You'd have to enable and refresh the publication to pick those changes up. So upgrading each node doesn't block writes on the other node. So in this unidirectional example of upgrading a logical replication cluster, the performing any activities on one doesn't block activities on the other. In this next use case, on a physical binary streaming replication cluster, we upgrade a physical replication cluster from 17 to 18, and note we're using a new PG17 tool called PG Create Subscriber, and this allows us to convert a physical standby into a logical replica. And it also automates steps to create publication for all tables and then create a subscription with copy data on to synchronize the data. In other words, we don't have to, by converting an existing physical standby to a logical replica, we're missing those steps. So in step 1, we stop the physical standby on node 2 and run PG Create Subscriber. And by converting a fully synchronized physical standby, we avoid the lengthy data copy process necessary otherwise for a logical replica. And all tables in the specified database are included in the logical replication setup. So you must ensure that the publisher can config items, max replication slots, max spool senders on the publisher are large enough for the increased number for the number of databases to replicate. And also the max worker process is greater than the number of databases on the subscriber. And using the PG Create Subscriber, a publication and subscription pair is created for every database. So in step 2, we upgrade the new PG17 logical replica on node 2 to PG18 using PG upgrade. And then we start up the new PG18 logical replica on node 2. And note that it was previously a physical standby, but of course now that we've converted it to a logical replica, it allows reads and writes. So in step 3, we stop the primary on node 1, and in step 4, we reinstate node 1 using a PG-based backup from the primary on node 2. And in step 5, we drop the subscriptions from node 2 on node 2. It's no longer a logical replica. So we end up with both the node 1 and node 2 running PG18 and back up as a physical streaming cluster. So this slide just summarizes what the PG Create Subscriber process does to convert a physical standby to a logical replica. And as you can see, the target physical standby must first be shut down, and that you need to run PG Create Subscriber on the standby server for every database where there's writes to replicate. So also remember, DDL does not replicate with logical replication. So any DDL run on the publisher whilst the standby has been converted to a logical replica has to be manually applied on the subscriber. And this slide's comparing timings for data materialization using standard copy data synchronization for 10 tables of varying sizes versus using PG Create Subscriber to do the same logical replication readiness. And as you can see, once the table sizes are beyond about 500 meg, we see PG Create Subscriber significantly faster in achieving the logical replica and state. So it's just worthwhile considering, instead of when you do have to replicate, to convert first of all. When you do have to upgrade, to first of all convert to a logical replica. And this slide...
Sorry, we're running out of time.
Sure, sorry, yeah.
Yeah. Yeah, sorry, we're running out of time. Please, thanks, Vince. If there's any questions, you can ask him afterwards at the reception. There will be 2 tickets for drinks for everybody. If you don't want it, then please don't take it, so PGEU doesn't have to pay for it. And yeah, again, if you have any questions, please pick them up, and thanks a lot.
Thank you. Sorry, say again?
Are you going to upload your slides to the conference?
Yeah, I will.